Okay, so if you guys go to this link, right? So the test was originally taken in like December, late December, or early January, but this year because of like the whole COVID situation, they pushed it back to February, which means that we have a tad more time, like a tiny bit more time, um, like to actually go over, yeah, 2021. It's like it's either January or February of 2021 because the 2020 was like this January, which was like last school year. Anyways, so the registration is not out yet, but then I expect like everyone on the physics team to like register and take this exam, but we don't know like what format this will be in or whether the assistant principal of physics, Mr. Thomas, is going to sponsor it. So all the details are still being worked out. However, because the date is now set, that means I know I have like a tad bit more time to actually cover material. So then today my plan is to like finish stuff involving rotations, but then after today, I plan on maybe going back to some previous topics in order to revisit like problem solving, as well as like to give you some more problems, maybe give a couple more like mock tests to get you guys all ready. All right. Sound good, everyone? Is there benefit or like, are there any questions? Is there benefit of taking the F equals MA? Yeah, of course, because it is a very like cool experience. This is like a national. All right, so the F equals MA is on February 18th. If I'm gonna send the link. Yeah, I mean, of course, it's still considered like a national recognition if you manage to qualify for the. I don't listen to Leon. Um, like it's still considered like national recognition, and plus, if you qualify for the USAFO, you might be able to qualify for like the international physics exam, which is the International Physics Olympiad, and that's like a pretty cool thing. So I don't trust this website. This is the official F equals MA website. I don't know what you're talking about, man. Yeah, the page was updated in November. Um, I don't know. They might have made a mistake, but this is the official website. AAPT is the official F equals MA website. All right, so without further ado, I think Andrew said he was going to be a bit late, so I'm just going to get started. All right, share screen. Can you all see the whiteboard?
Yes.
Coolio. Okay, so today we're going to be doing moment of inertia primarily. Who is Julio? I don't know. Perhaps. Moment of inertia. So the moment of inertia is basically what we know as the analog of mass in rotation, right? So then, first of all, like, where is the first place that we saw like just mass? We'll get to that later. So where is the first place we've seen mass in physics? Like, where was the first time? Yeah, so force. So the first place we saw mass was in like F is equal to ma, right? So then basically it says that force induces an acceleration. But then like because we have this m over here as a product, right? That means the more force you have, the more acceleration it's going to cause for the object, right? However, it also states that like if you have a bigger mass, then it's going to take a bigger force. If you have a bigger mass, it's going to take a bigger force in order to cause the same acceleration. Because if you divide over by m on both sides, then you get like F over m is equal to a, right? So then therefore we can sort of imagine, or we can sort of imagine mass as a resistance to motion. What really is force? This is a definition or for well, we did this during dynamics, so the more specific stuff was said during that lecture, but like we actually said like force is equal to dp dt, and then there's like a mass portion, but then that doesn't matter to us right now, right? So and therefore, because of that, right, we can say, is that a definition? I'd say that's more of a discovery, but we can say that mass is resistance to motion, right? So in the same way, the moment of inertia, or MOI for short, is basically a resistance to rotation, or rather to rotational change, right? Okay. So then we also want it to react like proportionally with, we want it to react proportionally with force, right? And then the rotational analog of force is torque, as we covered in the last lecture. So therefore what we want is for the torque tau to be equal to the moment of inertia multiplied by the angular acceleration. Who is Arib Jamil? That's you. Okay, so then now how do we find what, so this is for a point particle, right? Let's assume for now that we're working with a point particle. So now what we do is we can say that I is equal to tau over alpha, right? Okay, so then from last lecture, what is the definition of tau that we came up with? Okay, yeah, radius cross force. All right, so radius cross force, which let's just say is like r cross ma, right? Okay, where these are vectors. And then what is our definition of angular acceleration? Uh, Derivative of omega, well, it's actually the second derivative of omega. Actually, yeah, it is. But then what about in terms of linear acceleration? Tangential acceleration over radius, good. So a tangential over r, right? So then that means we can put this down here. Okay. Now, like when you're dividing by a fraction, you can move this stuff up. So r cross ma times r over at. Right, so then the cross, you can, since we have constants, you can sort of, well, yeah, but I'm saying like uh, we're trying to define the moment of inertia, right? So yeah, by the way, we say that the moment of inertia is denoted by I, right? Or it's called actually the Greek letter iota, but then capital iota is the same thing as Roman letter I. So that's just what we use. All right, because the cross product is distributive with constants, and that means you can actually put, you can actually factor a constant into the cross product, right? So this is just going to be equal. And then AT and AT, they cancel out. And then the R gets multiplied in. So we just get mR squared. Okay. So therefore, the moment of inertia of a point particle is just mass times the radius squared, where the radius is the distance between the axis and the particle. Okay, so any questions so far? Oh, okay. I'm going to take silence as a no. Yeah, as no questions. Now, what about moment of inertia for a system of point particles? For systems and distributions.
Well, so you said moment of inertia is m times r squared.
Yep.
Does that mean it's harder to move if the distance is greater?
Yeah, indeed. That's exactly what it means. And like this is actually a pretty important piece of conceptual understanding when we're looking at the moment of inertia of like certain things. Okay.
Hmm.
All right. So moment of inertia for systems and distributions. Well, actually, well, I wouldn't say pencil versus door because they have different masses, right? And that kind of changes some things. But let's imagine you have a door on a hinge, right? Okay, so then um so is it easier to push open a door from actually how do I do this? So let's just say you have like the same door, right? You have a piece of wood, but then, and then you either want a door on one hinge at the end or you want the hinge in the middle, right? So in which case is it easier to open the door? Like when the hinge is in the middle or on the left? And why do you think that is? All right, actually, I'll just say, yeah, I think Arib's right because the torque that's needed, is equal to like R cross F, right? But then if you're applying the force perpendicular, then R cross F is just equal to RF. And like if R is less, then that means the amount of force you need is actually also going to be less, right? What about work? We'll talk about work later, but what exactly do you want to ask about work?
Well, I was wondering because if you're going to have the one on the end, you're actually, if you turn a certain angle, you're actually going like a larger arc or like a longer arc. So wouldn't you need less force, less
Mm,
torque?
we're kind of assuming that like you're opening each door by like 90 degrees and then the arc would be the same. But we'll talk more about that later. Okay. We'll talk more about work later. Um, right. So if you have a system of objects, right, about some axis, so let's just say you have point particles like here, 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 and here. And then like these are all rotating about the same axis, right? Then you can add together the moments of inertia of the separate particles in order to get the moment of inertia of the entire system, right? So therefore I can say that like the moment of inertia of the system is equal to the sum of the moment of inertia of the particles is equal to the sum over all particles of mr squared, right? Where each m is going to have some specific index and each r is going to have some specific index based on which particle you're talking about. Moment of inertia is always, yeah, moment of inertia is always with respect to a specific object, or like a specific system and a specific axis, because the moment of inertia of the same object with respect to different axes is going to be different, because it's going to be like harder or easier to push open a door depending on where the hinge is, right? Okay. So what if you're not talking about a system of point particles, but you're instead talking about like a distribution of mass, basically like a continuous object, right? In that case, we have to replace the sum with an integral, okay, where you integrate over each little piece of mass. So to sort of visualize that, I'm gonna give you an axis and just some random object, all right? The thing with a continuous distribution of particles is that you can sort of think about a continuous distribution as a collection of many, many point particles. Like, each little part of this is just like another point particle in reality. And then we can say that if the mass of this entire thing is m, right, this thing has mass m, then we can say that each individual little piece of the object has a mass of dm, right? And then each dm is going to have its separate radius from the axis, right? This is going to be r. So then now when you're summing up the r squared times dm, this is the moment of inertia of your little piece of mass. And then when you sum all of them, then this sigma becomes an integral, okay? And this is for any general object, the moment of inertia is equal to the integral of r squared dm. Any questions so far? We learned this literally today. All right. Oh, Lucas is here. How are you? Okay. So you're probably not going to be asked to find the moment of inertia of a general object. However, there are a couple that I want you to memorize because these are important and common objects. For example, like your cylinders and your spheres and like all the symmetric jazz. So these are the important ones. So first of all, does it sort of, can I sort of say that intuitively the moment of inertia of a disk about its center is equal to the moment of inertia of a cylinder? Uh, so this is because you can just imagine a disk to be a cylinder. Yeah, you can imagine a disk to be a cylinder with like a very small thickness. Okay, which is why we can say that a disk and a cylinder are the same. Yeah, that's kind of the point. So intuitively, it works out. The disk is equal to the cylinder. And if the mass, we're going to say for all these objects that mass is m, right? Then the moment of inertia of a disk and a cylinder is equal to half of mr squared, where this is equal to r. Okay, and then for a hoop or a hollow cylinder, about its center like this, this is equal to just mr squared, right? Where this is r. For a solid sphere, actually, I'm gonna do that later. Hey, Andrew, how are you?
I'm good.
If it's a disk, then it's a cylinder. Okay, so I'm saying that a solid disk is the same as a solid cylinder because you can just say that a solid disk is a solid cylinder with very little width. Well, I'm saying like the proofs of these, so assuming the elemental mass is the same along any line parallel to the axis. The element, okay, so I'll go through, so all of these can be proved using this sort of generalized formula for moment of inertia, right? Like, so we're not going to be doing like too much calculus, but then I'll do an example of the proof of like one of these things, and then you can sort of think about how to get the others. But then, you know, I'll tell you, but then like, you know, the 1/2 comes from this integral. And then like any one of these formulas comes from this integral as well. Like the projection of a disk. What do you mean by the elemental mass?
I meant like just like an increment of the mass.
An increment.
Like if you were to take like a line like parallel to the axis through either of them, like the mass at that point intersecting that disk, that like increment would be the same as like if you take a line through the disk, it would be the same. It's the same sort of idea.
Oh yeah. Yeah, that's basically it. So then so like what you're basically saying is that like the density of the cylinder is the same, right?
Yeah, pretty much. It's
Yeah,
just
okay.
like
Yeah, so of course like all of these are assuming constant density. So which is why we can say that the disk is the same as the cylinder and the hoop is the same as the hollow cylinder. Right, okay. So the hollow cylinder is equal to mr squared. I'm actually going to show you how to get like this one, right? Because this one's pretty easy to prove. So what we want is this like Gauss law? Not
No, Gauss's law is very different from this.
Gauss's law is choosing a surface and then calculating flux. But
yeah, that's
in here, the surface, or rather the object, is given to us, and we're just taking the integral. Wait, so first of all, like, do you understand where this integral comes from?
I understand the integral, but like those other two formulas, I don't understand.
okay.
Okay,
So
I have
what
a
other two
couple of
formulas?
no's.
On the next page, the two, the one with the 1/2.
Oh, okay.
Yeah, wait, we'll get to that. We'll get to that, but then we have two no's in the chat for. Okay, so do you understand where like mr squared is from? Because we're just saying that we want tau is equal to I alpha. So then we took tau and divided by alpha and we got mr squared, right? Is that clear to everyone? I get a yes or something?
Wait, why is tau over alpha mr squared?
Because tau is r cross ma, and then alpha is a tan over r. And then we just canceled out the r, and then we get, we cancel out the a, and we get is equal to mr squared.
Okay.
Cool, okay. So from mr squared, we can say that because the moment of inertia of a point particle about an axis is equal to mr squared, then we can say that the moment of inertia of a system of particles is equal to the sum of the moments of inertia of the point particles, right? But then, for a continued distribution, we can view like a continuous object as a collection of point particles. And then if each a little mass element, if each little piece of the object has a mass of dm, and the entire thing has a mass of m, right? Then we can say that the moment of inertia is just equal to the sum over all mr squareds, which is dm r squared. And then the sum of all these is just the integral over the object of r squared dm. Okay, any more questions? All right, I will move on in that case. So I'll show you how like this integral goes for like one of these objects, and then the other ones you can try by yourself as exercises, or like, I don't know, you can take it for granted. Okay, so here what we want to find for the hoop, we're gonna go with the hoop, right? Because you can generalize the hollow cylinder from the hoop by just like stretching it along an axis. So we want the integral of r squared dm over the object, right? And then it's about an axis through its middle. But then what do you guys notice about the radius of every single point on the hoop with respect to the center? R is constant, that's right. So that means R is not actually dependent on M. R is just a constant, which is why we can factor it out of the integral, right? So because R is equal to big R, that means we can factor. That means we just get R squared times the integral over the object dm. And if you sum all the little mass elements, then you just get the total mass of the object, right? So this is then in turn equal to mr, or mr squared, right? So this is how, and then you can derive like sort of every other formula for the moments of inertia based on this integral. And then this is one of the simpler examples of how you do that, but you know, you can try them out on your own time. And then we'll just be giving you the moments of inertia for other objects. So, all right, so for sticks, right, if the stick has length L, then if it's about the end of the stick, then the moment of inertia is equal to 1/3 ml squared. And if it's about the middle, then it is equal to 1/12 ml squared. Not 1/2, 1/12. What else?
Are we talking about, are we gonna look at spheres at all? Or do you want to just
Yeah, we'll
ignore
look
them?
at spheres.
Okay. Well, fundamentally, just before we move on with these, yeah, all of the formulas like the 1/2, 1/3, that's what we call the shape factor of the individual shape. That's what we really calculate for the integral, because we know mr squared or ml squared is going to be common for every single one of these moments of inertia, just because of what the moment of inertia is. So yeah, you can memorize these shape factors if you want to. They're useful to memorize, like at least the basic ones. There are about, I think, 6 to 8 basic ones, something like that. Definitely for the F equals MA, you're not gonna have to calculate them. I think there's only one problem where you really needed to calculate it. But yeah, you can just memorize a lot of these shape factors. Like a solid sphere, the shape factor is 2/5. A hollow sphere, it's 2/3. For a plane, a disk, or a cylinder, the for a disk, sorry, it's 1. For a cylinder, it's 1/2. Like that's what we really need to memorize, because mr squared, ml squared is going to be common to all of them. So I'll let Alvin finish up with the shape
Wasn't there a
factors.
7/5? I don't think so. Unless I'm missing, unless it's like in one of the shapes that I haven't drawn yet.
Well, have you tried the axis being through the edge of the disk?
the edge. Well, yeah,
So,
but
like,
that is something for later. The
okay,
parallel axis theorem,
parallel axis
but that
theorem.
will be later.
Yes.
So
Parallel axis theorem allows you to calculate stuff for things that you don't know.
yeah, the hoop through like the middle, like this way, is also equal to mr squared. Which
A
is
re
pretty surprising.
So we don't look at any other points on the stick. Just well, for us, we don't look at them just because it's a lot to look at, but also because we like to fudge things. If it's closer to the edge, we'll just assume it's at the edge. But yeah, just for now, look at just the edge in the middle.
Okay. Another important thing to keep in mind is that the moment of inertia is additive, right? Which means that, if you have some axis and then you have like a disk going through the middle, and then you also have, I don't know, what's another object? You have a stick, right? And then you have like this weird contraption, and you want to find the moment of inertia of the entire system, then you can just add these two because of the additive nature of moment of inertia, right? So I total is going to be equal to I of the disk plus I of the, or iota of the stick. All right, so this is pretty important to keep in mind. All right, cool, I'm gonna let Andrew continue. New page.
Yeah, my bad. Hold on. So the overleaf is not, the notes are not behaving. They're not compiling. So all I see is the source code. Um, so let's see. So what are we up to? Okay. Alvin, if you could take like, I guess one more section while I figure out why this thing is behaving, that would be wonderful.
Hmm.
While that happens, I will try to compile this.
All right, I guess I'll give you guys a practice problem. So let's say you have a disk that is solid, but then you cut a hole in the middle of the disk, right? And let's just say that the radius of the big disk is r, and then the radius of the cutout portion is r over 2, right? And then this is all solid. All right, so through the axis, through the middle of like, so this is called a washer, I believe. So about an axis through the middle of the washer, find the iota of the washer. All right. Oh yeah, and let's just say that the mass is equal to m. The mass of the washer is m. All right. So y-axis should not be point. Well, anything rotates about an axis, right? So you can like DM me the answer, and then we can go over the question. Yeah, the mass of the washer without the center is m. And oh yeah, of course, you can assume constant density. Hold on. Ooh, fancy fractions. Um, okay, so you have minus da, 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 da. Wait, those are squares. Why do you have the third term? Where is the third term coming from? Actually, yes. No, no, you can't really say that. Wanjang, pick one. Because we're not really, you can't really say that like the inside is a hollow, well, the inside is a hollow circle, but then it's also part of the disk. So then you can't like add it, you know, because you're sort of like adding the hollow circle on top of the hollow, on top of the disk when the circle is part of the disk. All right, 15/32. I think that looks right.
Bro, why you said it out loud?
Because I think we have enough answers to go over it. So Lewis, do you want to present on the board?
Oh, I did it on paper, but if
No, but like, can you do you have like
remote control.
no, like you can annotate.
Oh, sure. One moment. Let me see. Um. So basically, what I did was you have this outer part, which is like, come on. Wait a second. I don't think my answer's right. That doesn't seem right. Is it
Okay.
right?
I'm actually not sure, but uh, it, it shouldn't be like too pretty. So
No, but the problem is for mine, it would mean it would be 3/4 of the mass, so it's wrong. It has to be 5/4 of the mass and then minus the fourth in the inside.
yeah,
So
that sounds right.
yeah, so mine is wrong then.
Okay. Arib, do you want to present?
Yeah, scratch that answer I sent you. I have a different one. Okay, so, and let me annotate real quick. Okay, so I set up a ratio. It was like, I know the mass density should per unit area should be m over pi r squared, and that should equal the mass density over pi r squared over 4. And I just did r over 2 whole squared, and that's r squared over 4. So then I multiplied m, to solve for x, I divided m pi r squared over 4 by pi r squared. So I just put that in the denominator.
Wait, hold on. Shouldn't the mass density of the entire object be like over the area though? So it should be like pi r squared over pi r squared minus pi r squared over 4.
What?
The mass density.
Oh, you're right. You're right.
Because
Okay.
we're dividing mass by
I got you. Yeah. The mass of the m isn't over pi r squared. It's over the remaining after you subtract. Yeah.
which should be 3 pi r squared over 4. Right, so like
Oh, yeah. 3 pi r squared over 4. Yeah, because 3/4.
Yeah. So 3/4. And
Yeah.
I'm gonna erase this. Okay, so this is the mass density. All right, now what?
Can you write for me?
Okay, yeah, sure.
Okay. That should be the same for the center, which is m over pi r squared. M over 4 pi r squared. Sorry, m over pi r squared over 4.
So like the middle part, which is empty, you're saying like if it were filled, then it would
Yeah.
have a mass of m over 3/4 pi squared, which is the
No, 1/4 pi r squared.
1/4. No, but then like you're multiplying by the area, right? Which means
The middle, it's
no, but like it doesn't actually have a mass, right? So you're saying
yeah.
if it were the same density.
Oh, sorry. It's x. That m should be an x. We're solving for it, right?
You're solving.
Aren't we solving for it?
No, you're trying to find the moment of inertia of the washer.
Yeah, I'm trying to find the mass of the middle, and then I'll find the moment of inertia.
Okay. So it should be m times 3/4 pi r squared equals to.
That m should be an x because we're solving for the.
All right. So just like restate your entire thing then.
Okay, x over
Mhm.
1/4 pi r squared.
Pi r squared is equal to.
M over 3/4 pi r squared.
All right. And I can kill these off. And then you get what? X is
equal to 4/3 m.
4/3 m.
Yeah. And then we know that the
right.
moment of inertia should be half.
Wait, Arib, that doesn't look.
What?
I think it should be m over 3, right? Because math.
Wait.
Oh, you're right. Yeah, you canceled out the 4. You're right. Yeah, math. Crazy. Okay, x equals m over 3, and then we know that assuming the center were filled, the moment inertia, the whole thing would be half m r squared.
Okay. So first of all, we have to.
But m is different, right? M is going to be m plus m over 3, so 4/3 m.
Right. But I think it should be helpful to establish first that the I of the washer plus the I of the middle disk
is equal to the total.
is equal to I of the big disk, right?
Yeah, assuming it were filled.
So then therefore, so the I of the washer is equal. So what is the I of the middle disk?
It's going to be 1/6 m r squared.
So 1/2 m over 3 r over 2 squared.
Oh, yeah, my bad. Yeah. That should be a 12th. Oh, wait, no, 24th.
Yeah. Let's just keep it like this for now. And then what is the I of the big disk?
It's going to be 1/2 times 4/3 m times r squared.
R squared, right? So now we can subtract these, and then therefore we get I of the washer is equal to, this would be 2/3. Yeah, 2/3.
4/6 minus a 24th.
And then subtract 1/12. No, 1/24.
Yeah, 1/24.
MR squared. And this is in total equal to 7/24 MR squared.
No, it should be 15, I think, because you multiply by 8, right? 16 minus 1 is
Oh, yeah,
15.
15. Sorry. I'm bad
Man,
at
fractions are really hard.
fractions are hard. 15/24 MR squared. All right. So this is basically using like the main idea here is using the additivity of moment of inertia in order to find like the moment of inertia of more complex shapes. Okay, so any questions? I see a couple of direct messages. Let me read through them. All right, Lewis, you got 15/32, which was close. You might have missed like, actually, yeah, you got it afterwards. Good job. All right, any more questions about this problem, this small problem over here? I agreed with 3/8 because I didn't know the answer, but it looked kind of, I don't know. Oh, it should be 5/8 because you can reduce. Okay. If there are no more questions, then let's move on.
Okay, so I think we stopped at the parallel axis and the perpendicular axis, right? So, excuse me. So as Arib had already guessed, yes, we're going to be going over some stuff with the parallel axis theorem. So, yeah, moment of inertia really has only two theorems to know. So we're going to start with the easier one, the one that actually pops up a lot more, the parallel axis theorem. So yeah, and in order to understand this theorem, we have to consider a special set of cases. So for the parallel axis theorem to work, we need to consider two parallel axes. I mean, two parallel axes where one of the axes, and I'm going to try to annotate this as best as I can, one of them going through the center of mass of an object, and the other one just going through a different point. So because this theorem applies to any object, we're going to literally just draw the weirdest object we can. And yeah, so here's our object. And let's say its center of mass is somewhere here. Here's its center of mass. Let me denote it with a different color. So here's our center of mass, C. And we're saying take one axis through the center of mass, and then another one just going through some random point P. So let's pick this point P. And this axis is going to be parallel to this one. So we now know that we can describe two different moments of inertia. We can describe the moment of inertia, and we'll actually denote this Cm. So the moment of inertia of this one is going to be iota Cm. The moment of inertia of it going through this axis is going to be IP. And the mass of this system is going to be m. And we're going to describe this distance as d. So now the parallel axis theorem says that the moment of inertia of an object of the system through this parallel axis is equal to the moment of inertia of this object through its center of mass plus md squared. There's our parallel axis theorem. And this works for us for any system where the center of mass, this works for any system, like with mass and a center of mass. So that's our parallel axis theorem. So now, could someone like in the chat, like type out why this is a useful theorem? Because, you know, we don't just make theorems that are completely useless. So why is this a useful theorem?
The line, okay, so ICM is the moment of inertia about any axis through the center of mass. Be shifting a fulcrum.
Can I find I for any point?
Yeah.
Yes. So the thing is, the moment of inertia works for a system at a point about an axis. So if you have the moment of inertia of the center of mass about some axis, you can find the moment of inertia about for any point as long as it's about an axis that's parallel to the initial axis. So does that kind of make a bit more sense? Okay, shifting the fulcrum. What if it's higher? Well, I mean, here we have point P is higher than the center of mass. Or are you referring to something else?
Well, the axis is a line, right? So then there's no real like higher or lower because it extends to infinity. Yeah, and then what's important is that they're parallel.
Yeah,
and not
exactly.
the positions of the points in which they pass through.
Yeah, so this could be a bit of a misleading diagram. Let me draw it slightly more. So let's say we have an object that looks like this. It's three-dimensional. Right? We have a three-dimensional object. So let's say that this is our center of mass. And the axis goes like this. It's kind of the best line I can draw without using the straight line tool. And then we can pick any point in this within this boundaries of this object P. And we can calculate the moment of inertia about an axis parallel to the initial. So height, location, as long as it's within the boundaries of the object, there you go. Sorry, kept Borad problem. Jesus Christ. All right, let's hope you didn't spill anything on your keyboard. Okay, so there is a way actually to derive this formula. This formula doesn't come from nothing. So let's derive it. So again, we will start, and we'll use kind of like a coordinate approach, because the big issue, and why isn't it letting me add a new page? Alvin, can you only add a new page? Or do I have to exit the annotation tool? Ah, there we go. Okay, so the one problem with this, like, is the center of mass can be literally anywhere in the system. So to make things easier for us, right here, we're gonna say derivation of pat. That's actually not going to work because perpendicular axis theorem is also pat. Let's say pat.
Yeah, fun fact, it's also called Steiner's theorem in Europe because that's the guy who derived it.
Steiner's theorem. So we can call this also ST, Steiner's theorem. Yeah. Sure. All right, anyway. Let's say that the center of mass has coordinates 0, 0. Like, we're just going to stick the center of mass at the origin. Make it easy. And so this is the coordinates of our center of mass. And we're going to examine also every single individual mass element, because then P is just going to be an arbitrary mass element. So is going to be the location of a given mass element. So P, or as we call it, a mass element Mi, is going to have coordinates xi, yi. Okay. And this is going to be perpendicular to the xy plane. And this is going to have an axis of rotation through, it's going to have an axis of rotation, this one through the center of mass and perpendicular to the xy plane. Okay. So now, oh, actually, my bad. This just denotes any mass element. P, we're going to pick specifically. P we'll specifically pick P as having coordinates AB. This is the coordinate of our arbitrary point. So now we can calculate the distance to any the distance to any mass element from the center of mass. So if we have the center of mass here, this is our CM. Here it's 0, 0. Here we have our mass element Mi. It's going to have coordinates xi, yi. Arib, let's try not to spam the chat. So we have this. So by the Pythagorean theorem, oops, this distance is just, well, root xi squared plus yi squared. Wow, I nailed the size of that square root. Okay, so now we can calculate, using our formula, the moment of inertia through the center of mass about our given axis that's perpendicular to the xy plane. So our center of mass, iota cm, is going to be equal to, well, we take all of these mass elements and multiply them by the square of this distance. There we go. That's our mr squared. This is our r. And we do this again for each mass element. And that's the moment of inertia through the center of mass. Now, we can say the exact same thing about P. So now, to calculate the moment of inertia through point P, we now have to take a different distance to point P. So instead of having xi squared plus yi squared as our distance, we're going to have xi minus a squared plus yi minus b squared. Does it kind of make sense where this comes from? So we declare any point as 0, 0 to make it easier. Yeah, because think about it. You know, coordinates describe everything relatively speaking. So like if you pick any single point and call it 0, 0, everything else can be described relative to that point. And when it comes to moment of inertia and when it comes to most things in physics, we deal with it relativistically. So you call this point 0, 0, that means any point to the left is going to have a positive x coordinate. Everything to the everything to the right is going to have a positive x coordinate. Everything to the left is going to have a negative x coordinate. That's it. It's that simple. So yeah, you can declare any point as 0, 0 because we're not limited by anything, structurally speaking, because what we're really talking about is where we center the center of mass. It's the same way as when you're calibrating a weight, for example. Like if you have multiple things that you're trying to take the weight of, what you typically can do is you take the weight of the entire system, you set that as 0, and then you take off your desired weight. And then you're going to get a negative number, and the absolute value of that negative number is the weight of your object. So it's the same thing. We deal with it relatively. So it's the same thing. We can do that. Does everybody understand why we can just pick a random point as 0, 0 and just solve the problem from there? I'm gonna take the silence to mean yes. Okay. And everybody gets this distance, xi minus a squared plus yi minus b squared, or the square of the distance. So the moment of inertia, iota through p, about the exact same axis, that's going to be, well, is going to be, again, the sum of all these mass elements, mi, except this time we have, excuse me, xi minus a squared plus yi minus b squared. It's the same mr squared. Okay, that's a lot, but thankfully, we know a little bit about expanding things, and we can expand this. So let's expand our moment of inertia through p. So iota p is going to be equal to, well, I'm going to save you guys the algebra trouble, so I'm just going to do all the algebra right now. Xi squared plus yi squared minus 2a, some of the mass elements, mixi minus 2b miyi plus a squared plus b squared sum mi. Does everybody kind of sort of see how this works? We're just expanding it. Xi minus a squared expands to be x squared minus 2axi plus a squared. And yi minus b squared expands to be yi squared minus 2yib plus b squared. And because these points can be completely random, they're independent of anything, so we can just treat them as constants and take them, a and b, I mean, because a and b are completely arbitrary. They're not dependent on the system, so we take them out. And we have this. Okay, so notice then, what's this? Just type in the chat, like, what's that? Iota Cm, exactly. That's the moment of inertia of the center of mass. So this is just iota Cm. Okay, now what's this? We're looking at the middle two terms now. What are those? Momenta. Okay. Well, there's no velocity here, so it's not really momentum.
Okay, just to clarify, so we're dealing with three space here. Okay, so we have the x-axis, a z-axis, and then a y-axis, right? Is that how you're supposed to denote things? Probably is. So what we're assuming here is that if we have like our object, that's not that good of an object. There we go. If we have an object and like we place the center of mass at the middle, right? Then this is the CM. Then we're assuming that the axis of rotation that we're working with here is the z-axis.
Exactly.
Right? And then the point P is arbitrary. So then it can be in the object, it can be out of the object if you want. But like, if P were here, and we basically draw a line through P that is parallel to the z-axis. right? And then this is trying to find the moment of inertia through this new axis. So the moment of inertia through the z-axis is ICM, and then the moment of inertia through the new axis that we define here is I sub p. And then the xy distances that we're talking about here is like, it's just the like the distance of the point, the distance between the center of mass and the point's projection onto the xy plane. Okay, so this is the, I'm gonna switch colors. So this red line over here, this is like the xy distance, which is, what we have over here, all right? Because we're talking about like the distance from the axis, which is what we want. Okay, carry on, Andrew.
Okay. So yeah, I hope that clarifies better what we visually are talking about. Yeah. So yeah, anyway, these middle two terms, well, let's consider what we're doing here. We're adding up the, was there PAET?
There was no p set. Okay, here's the deal with the p sets. I don't want to give you work over Thanksgiving, and we're gonna have like a small a small contest next time. So I'm gonna be making a rotations p set due like after next week. So it's gonna be like next Monday.
So December, next Monday, so December 8th, something like that. No,
Yeah.
sorry, December 7th. Yeah.
6th, Monday. So 7th.
Yeah, 7th. And speaking of contests, the F equals MA is nearing. We still don't have any information as to when
No,
it is.
I made an announcement before you came. It's on February 18th now.
Oh, they've announced it officially. Oh, nice.
Yeah, we'll talk about it more later, but
Yes. I don't think that overlaps with the AMCs. So I think we'll be good. Yeah, it doesn't overlap with the AMCs. We're good. All right. Anyway, back to this. So let's consider what we're doing here. So we're summing up MIXI and we're summing up MIYI. Well, where have we seen this before? We've seen this before when it came to calculating the center of mass. So by the definition of the center of mass, this actually will cancel to 0. You guys can verify this for yourselves by looking at the definition of the center of mass. Just because we're running a little bit short on time with, we have another theorem to go over. So what about this? What's a squared plus b squared? A squared plus b squared is the distance to point P from the center of mass, right? So this is just our, as we defined it, D. This is our D. And what is the sum of all the mass elements in a system? Well, it's the mass of the thing. So this is big M. So this is equal to ICM, or iota CM. Oh, sorry, this is D squared because square root is a thing. Plus MD squared. And thus our proof is completed. And yeah, again, this proof works universally because it has absolutely nothing to do with the shape of the object. It has nothing to do with anything. And it's not dependent on anything. Because again, you can always pick any point to be your center of your coordinate system, to be the origin. So this works for anything. We're assuming uniform density. And uniform, uniform density, uniform mass displacement. So yeah, for any system with a uniform mass displacement, the moment of inertia through a point about an axis parallel to one through the center of mass, you can calculate it with this formula. Any questions? Nope. Okay, awesome. Is this on F equals ma? Yes. Parallel axis theorem will come up on the F equals ma. The perpendicular axis theorem, not so much. The perpendicular axis theorem, you might see it maybe on a problem. You are very likely to see at least 1 or 2 parallel axis theorem questions on the F equals ma. This is extremely useful when you need to calculate some sort of moment of inertia, because the F equals ma loves forcing you to calculate the moment of inertia of an object through some sort of axis. So this is the way to do it. This is a nice way to calculate it. It's sort of like ICM plus inertia with respect to CM. Pretty much. Yeah, that's kind of what it is. So yeah, this is going to pop up a lot. So if you really want to, if you want to be solid on a lot of moment of inertia questions, you need to know this theorem. You need to understand its implications, and you need to understand how to apply it to calculating other moments of inertia. There are a ton of questions, practice questions that we can throw at you. So we're actually going to take like a little break right now. We got about 10 minutes until 6 o'clock. When we come back, I'll quickly describe the perpendicular axis theorem, which is also useful, not as useful, but useful. And then we'll finish off on a bit of rotational energy, and we're going to wrap up with some angular momentum. Hopefully we should have time for that. So see everybody back here at 6. So we have moment of inertia just iota, right, through a point on this axis, and then we have another one that's perpendicular to that one, iota a, and then we have a third one perpendicular to that one, iota b. It says that iota a plus iota b equals iota. That's your perpendicular axis theorem. The idea is if you have 3 mutually perpendicular axes, if you have an axis, you can describe its moment of inertia about that axis through 2 moments of inertia that are mutually perpendicular to each other.
Right, just a note for perpendicular axis theorem though, it only works for 2D objects. Therefore, it works for like a disk, but not a cylinder. And it only like, like a puddle, I don't know. So like, if you can find if you can find the moment of inertia through like through x and then through y such that these two are perpendicular, then you can add these two and then you get the moment of inertia through the z-axis, I guess. All right.
And why is that? Well, it's very basic because, if you have 3 points, if you have 3 axes that are mutually perpendicular to each other, they kind of have to sort of intersect at a point because like otherwise it doesn't work. Otherwise, there are infinitely many possibilities. So the problem is you're only narrowed down to one set where they all intersect in a point. And at that point, you're basically just examining the moment of inertia on a flat surface. So that's why it only works for 2D. Well, there's obviously a more complicated and better reason for that, but I will leave that to you guys because again, this shows up on F equals ma occasionally. It's not super big because it's so limited, because it only works in 2 dimensions. But it's a thing that you should remember. You can describe the moment of inertia about some axis in terms of 2 moments of inertia that are mutually perpendicular to each other. What is the 3D version? You'll find out.
I don't think there is a 3D version.
Yeah, there isn't. So next page. That was quick. How much time I got? I got 25 minutes. So 25 minutes to talk about rotation and rotational kinetic energy and angular momentum. So here. Can someone guess what rotational kinetic energy is? Like the formula. So if I have, let's write out. So let's do this again. So okay, no, this tablet does not want to behave today. Bye-bye. Okay. I apologize for my horrendous handwriting today. But yeah, so if we have K translational, this is our translational kinetic energy, which is equal to 1/2 mv squared. What do you guys think rotational kinetic energy is? So I see a lot of people writing 1/2 iota omega squared, and that is right, 1/2 iota omega squared. Why? Well, I mean, moment of inertia is the angular equivalent to mass, and the angular velocity is the angular equivalent to regular velocity. But anyway, we can there's a better way to like well, yeah, that's basically how it's defined. Yeah, this is your rotational kinetic energy. And the work energy theorem applies the exact same way, except this time you differentiate the torque with respect to the difference of the angle. Why angular momentum mvr and not IWR? Well, the angular momentum, we'll get to that in a bit, actually. Let's leave it for that for now. So yeah, the work energy theorem works exactly the same way. You know, the work done is going to be 1/2 iota omega final squared minus omega initial squared, which is described by this integral, tau d theta. Because instead of integrating force with respect to the change in position, you integrate torque with respect to torque with respect to the change in the angle. So there's your rotational kinetic energy. Why is this important? Well, okay, Arib, you seem to have resolved it. Yes, there we go. So why is this important? Well, because if we have a rolling object, we now have to describe the kinetic energy differently. Because, you know, if we slide just a cube or a block down this way, what do we get? Well, its kinetic energy will increase. It'll be 1/2 mv squared. It makes sense. It'll increase. And that's how we describe things. You know, at the top, it'll have a potential energy, mgh. And as it speeds up, the gravitational potential will decrease because the height will decrease. And the kinetic energy will increase because the velocity will increase. Problem is, what if we have a sphere rolling down the hill? Well, that's a bit more complicated because now we have to take into account its rotational motion too. Can we not roll the cube? Good luck. Good luck.
I mean, like, actually, can we not?
You mean like
have it fall over like that over and over again?
you can, and there is a shape factor for a cube, for a square. That's more complicated. And yes, in that case, you will also have to be describing it in terms of that. But for now, we are just assuming that if we're dealing with a cube falling, it's just going to be falling. We're going to assume it's not rolling.
Yeah,
But
can definitely tumble, but then the rotation of a cube is actually very difficult to describe. So
yeah,
I don't think any contest covers it.
well, let's put it this way. The rotation of a cube on a flat surface is very difficult to describe. The rotation of a cube on this kind of surface is very easy to describe because it behaves in the same way that a circle rolls on a flat surface. If anybody's been to MoMath, they have seen the weird curvy circular patterns that the square-wheeled bicycles can roll in. And that's because they designed it in a cycloid fashion, semicircular fashion. And yeah, the rotation, then you feel like you're not bouncing up and down because the rotation is similar to that of just a circle on a disc on a flat surface. But yes, the rotation of a square on a flat surface is very difficult to describe. Yeah, so anyway, we're going to be dealing with simpler rotation for now. So if we have a sphere or a cylinder or a disc rolling down, not only does it physically speed up faster, not only does it move translationally faster, but it also rotates faster and faster. It spins faster and faster. So you need to describe that motion too. So to describe that motion, we also take into account its rotational kinetic energy. So K total, K tot, equals your translational kinetic energy, KT, plus your rotational kinetic energy, K rot, which is equal to 1/2 mv squared plus 1/2 iota omega squared. And at that point, you need to examine, your omega is always going to be V over R, but your iota is going to depend on what figure is actually rolling. The shape factor will depend on the actual thing rolling. The translational kinetic energy will always be 1/2 mv squared, no matter what object is rolling. Oh, sorry, not rolling. No matter what object is moving or falling. It doesn't depend on the shape, but your rotational kinetic energy does depend on the shape. So you have to be careful there, because a lot of people often screw the pooch and they say, 1/2 mr squared gets some sort of answer, and then they turn out to be wrong because it was actually a sphere rolling, not a cylinder. Friction is fiction. Okay, well, friction also doesn't depend on the shape, right? Friction only depends on the coefficient and the normal force. Friction. Yeah, so, I read. So friction doesn't depend on the shape. Friction just depends on that. The type of the friction might depend on the shape only if the number of contact, didn't I say? Yes, that was referring to contact points. Yes. If the contact points are dynamic, then it's static friction. But the problem is the formula for static friction isn't going to change. It'll just be static friction. The formula will still be the same, but the type of friction will be different. So yeah, that's a good clarification. The type of friction will depend, but why does the ball roll, not slide? That is a good question. No, but yeah, it's because the contact points change. Like it's pulled down by its own inertia. If Alvin, if you have a better answer as to why a ball rolls instead of sliding, go ahead. That's my answer, like on 3 hours of sleep.
Oh boy. Okay, so like I think this goes into another topic, which is rolling without slipping, right?
Mm.
So the basic conceptual understanding of rolling without slipping is that, so let's just say that the friction is equal to 0, right? So on a frictionless surface, there's actually no reason for the ball to start spinning because, if you look at all the forces acting on the ball, right? You have, the gravitational force acting downwards on the center of mass, and you have the normal force that matches it going upwards, and there would be really nothing else, right? So in this case, the ball is just going to slide.
Like a bowling ball on a rink. If you don't curve it, if you just push it, it'll slide.
Yeah, exactly. So that's why like a bowling ball would because a bowling ball and the lane has very little friction, which is why the ball slides more than rolls, right? Okay. However, let's just say that there is friction. Alvin ball, no.
I think Key Club did a bowling event, but other than that, no.
So
Um,
given So given sufficient friction, if we look at the surface, right, it's gonna have the same like gravity and normal force, but that we're not gonna worry about that for now. So with like mu sufficiently large, there's going to be a force that acts on the bottom point of the ball. But because it's like not a box, right? It's a circle, then it's acting on the entire point of contact, which is going to be only the bottom point for this ball, right? So therefore, we can draw this friction force acting on the bottom, F, right? Okay, but then because we know that force can create torque if it is not like through the center of mass, then the friction creates a torque that is R cross F. Right. However, and that's what's gonna start, and like that's why when a ball starts rolling down a surface with friction, like it's not going to slide, but instead it's going to roll, right? And this is gonna cause some angular acceleration this way. However, why it doesn't matter for like the friction can be as large as it wants, because well, so the friction can cause like a change in energy from kinetic energy to like heat, and then it's going to eventually stop the ball. But then at some point, it's going to start rolling without slipping, because the friction can only oppose the motion to a point where this bottom point does not move. But like because the angular acceleration still exists, that means the ball is still going to roll, but then this bottom point is not going to move for any value of the friction that is large enough. So therefore, this point on the bottom will not move. And the only choice for the ball, the only choice of movement for the ball to take next is the next point of contact over here, right? And then, which means that given large enough friction, each contact point can only be at the, each contact point can only be on the surface for 1 instant before the next contact point actually arrives on the surface, right? So then that's why we have rolling, that's why we have rolling without slipping. And then you can sort of think of that as like, if you were to cover the entire outside of the circle in like I don't know, like chocolate, or not chocolate. You cover the entire outside of the wheel with feathers, and then you cover the ground in tar, right? Then after it rolls for some amount of time, after it rolls for 1 rotation, you're going to see a line of feathers that is the same as the circle's circumference.
Because all of it will rub off.
Because all of the feathers are going to rub off on the tar, right? And then these are all going to be the same like density of feathers, I guess, because each point on the circle makes contact with the ground once per rotation, right? So then that's why, given sufficient friction, we will only have rolling without friction, rolling without slipping. And then eventually, the friction is going to, I guess, turn some kinetic energy into heat, and then the ball will stop rolling. But yeah.
Yeah, and also like this isn't as big a deal, but there's also you have to remember that there's air friction. So like, you'll have air pushing like this. And like with a flat surface, it's going to be pushing everything like this, right, evenly. So no part will move, but here, these parts are pushed on and these parts are pushed on. So it'll just start curving this way too. It's less, this is less useful, but like, yeah. That's why if you blow on it, it'll also start rolling at some point. Anyway,
Any questions about rolling friction? and then how it causes rolling without slipping at the extent of it. All right. Unless
So
no questions.
I guess that leaves us time for like just two final things. So we've talked about, solving problems regarding just regular forces, and it's not letting me make a new page. Is not like
I will do that.
okay. We talked about problems regarding forces in a system. So we talked about, what can we always say? Oh, Arib has a question. Yes, Arib.
So when it rolls, the friction exerts a torque, but so the contact point starts rotating, backwards, whatever, the opposite direction of the motion, or forwards, but the ball or disc itself keeps rolling forward.
Yeah.
So like the friction force is equal to mu times the normal force.
Mhm.
And since that's acting on a point of infinitesimal mass, it goes backwards.
No, like the friction acts on a point on the disk, right? Which causes a torque on the entire disk and not just like, I guess, the point itself. Because if the point were to act like independently of the disk, then it would fly off, I guess. And that's an assumption we're making here, is that like the disk stays intact. So I don't know if that was your question, but
No, I mean, like, I found it interesting how the contact point can move in that direction. Like, it can have a torque, but at the same time, the disc itself can move forward.
well, okay, so then because the disk itself is moving in a direction like to the right, right? But then this is translational motion, and it doesn't have a lot to do with the rotational motion of the elements around the center. Do you understand?
Okay, got it. So the translational forces have nothing to do with the rotational forces, unless they're on the edge.
Yeah, kind of. So, actually, when they are rolling without slipping, you can relate the translational motion with the rotational motion, but then, like, fundamentally, they don't have too much to do with each other. Okay, does that answer your question? Cool. All right.
Okay, so awesome. You can just make a new page. Yeah. So we talked about forces and like calculating different forces back when we were talking about kinematics and when we were first talking about about Newton's laws and dynamics. So what did we say? We said that the net force, the sum of all the forces in your system, is going to be 0, right? For a closed system. Because yeah, that's how we defined it. Conservation of momentum, conservation of energy. Nothing is added or like removed from the system. So the net, all the forces in the system will add up to 0. So we can say that for a closed system. For a rotating system, we can say the exact same thing about the torque. So the net torque, the sum of all the torques, has to also be 0. And the sum of all the torques can be described as, the rotation of the center, the moment of inertia of the center of mass of the system times the angular acceleration of that system too, center mass. But yeah, the same way that we can say that the sum of the external forces of the system is 0, we also can say that the sum of the torques is 0. So if we have a rotating system, and this is where statics come in, right? So if you have, for example, a seesaw, right? And I weigh some sort of mass m1, and I don't know, Alvin weighs some sort of mass m2. The question is, where do we put the fulcrum so that the seesaw doesn't move? That's a statics question, right? Because what happens, if the let's say I weigh more than Alvin because I have not been exercising all of quarantine. So let's say M1 is bigger than M2. Like if I move it too far from M1, what's going to start happening? I'm going to start weighing it down and it's going to start moving like this. Oh, so there's going to be a torque there's going to be a torque here. And the same thing happens if I move it too close, if I move it too close to me. If I move it too close to me, M2 is going to exert a torque so and move this way. So what has to happen? We have to balance the torques. This torque has to equal this torque. So the net torque has to equal 0 if the object isn't moving. Ugh, sorry, give me a second. Here we go. Yeah, the net torque is equal to 0. So this opens up just a whole new class of problems with balancing torques and statics and like how much of a force do you need to exert in order to tip a cow? Like that's balancing torques. Because basically, you know, when you're talking about cow tipping, what are you talking about? Well, you have your cow here. This is a little butt. And you are tipping it, you know, at a certain angle. Yes, we're tipping Bessie. This is the back of Bessie. And you know, we're tipping the cow, and the cow needs to, you know, tilt at a certain angle. So like, let's say that this is your pivot point. This is your pivot point. So we're exerting the torque here, and we want Bessie to tip. And so we say, okay, if Bessie's not tipping, like what is the maximum amount of force we can be exerting? What is the greatest torque we can be exerting such that Bessie doesn't tip? Well, it's gonna be, you know, we find it, the torque is 0, the net force is 0. And we find that, you know, anything slightly bigger than that will tip Bessie over. I don't know, it depends on the mass of the cow. But anyway, the point is we can calculate it. Yeah, so whenever you have a rotation problem, you have a system of 2 equations. You already automatically have 2 equations. You have that the sum of the forces in the system is 0, and you have that the sum of the torques in the system is 0 if the object isn't moving. So that's just important to know. And in the last 3 minutes, I'm going to introduce angular momentum. So we've talked about a lot of rotational analogs. Can you make one more new page, Alvin, or is 10 the limit? No, it's not. I guess 20 is the limit. So we have one final thing. So we talked about a lot of rotational analogs. So we have the rotational analogs of all the systems of you know, your position, your velocity, your acceleration. You have the rotational analogs of the kinematic equations. You have the rotational analog of force, that's torque. Rotational analog of mass, that's your tensor moment of inertia. We talked about all those. So there is one final rotational analog, and that's angular momentum. And angular momentum, you know, in the same way that to get all the other rotational analogs, we cross R with something, with the thing. To get angular momentum, L, it's denoted L, we cross R with R momentum. This is R cross MV. So normally we just describe this as MVR. So normally we have L equals MVR. And, you know, in the same way that force is the derivative of momentum with respect to time, we have torque is the derivative of your angular momentum with respect to time. And in the same way that momentum is conserved in a system, in a closed system, angular momentum is conserved in a closed system. That's why if I spin, let me see if you can you guys see me spinning? If I spin like this, all right, you guys can see that. So let me spin a little bit for you guys. So it's the same way that if I spin like this, and then I pull my arms closer together, I'm gonna start spinning faster. I'm gonna slow down, spin faster. I slow down and faster. That's because the angular momentum is the same, right? If the angular momentum is conserved, right? I have mv r big R, because I'm outstretched. I'm basically a big sphere, and then I bring myself closer. The R is now much smaller. I have mv little r. So if little r has decreased, then that means that the velocity has to have increased.
I think a better example
Give me a
would
second.
be the figure skater, right?
Yeah,
So like when the figure skater has like their arms out and then they bring them in all of a sudden, like Andrew just did, it's much more apparent that the spinning is a lot faster. So
Yeah.
yeah.
So in any case, yeah. So if the radius decreases, the velocity increases. So it's important. So, and just like the impulse momentum theorem says that delta p is f net delta t, we have delta L is tau net delta t. And I think that's it. We don't have any, we are out of time, and that we've basically covered everything we wanted to cover. Rotation's a big and annoying and scary topic. There's a lot to cover, there's a lot to know, there's a lot to memorize. But what's important, memorize the big shape factors for moments of inertia. There are about 6 to 10 of them. Just memorize them. They're pretty useful. Parallel and perpendicular axis theorems, you memorize them too. More importantly, memorize parallel axis theorem, because that one is a big one. Perpendicular axis may come up occasionally, but it only works in 2 dimensions. And remember rotational kinetic energy. That's a thing that you cannot forget about when you are talking about the energy of a system that's rolling. And yeah, angular momentum. And the net torque of a system is 0 if nothing is moving. That's the basis of statics, that the net torque of a system is 0 if nothing is moving. And that's it. So yeah, we want to wish everybody a happy Thanksgiving. Remember, no classes until then, and no, we'll be hosting some sort of 4:30 Saturday. We'll have office hours. And what else? Yeah, we won't have any P sets due until December 7th. And remember, guys, F equals MA is going to be coming up on the 18th of February. So you guys might want to start prepping for that. We will be sending out some sort of registration link probably after Thanksgiving. And yeah, that's about it. Alvin, do you have anything to add?
Yeah, next week we'll be having a small contest, so that'll be cool.
Should I take F equals MA? Yeah, everybody should take F equals MA.
Everyone should take F equals MA.
It's okay. We're not going to be judging you based on what you score. Like, it's just everybody should at least take the F equals MAA. The B is optional, but in the same way that the math team requires everybody to take the A, just take the A. Like,
There's only one this year.
oh, there's only one this year?